Welcome back. We were discussing in Fundamental of Electronics about the power amplifiers. We have covered the class A power amplifier, and in this lecture let us see about the class B and class AB type of power amplifier. We saw that in class A power amplifier that it will be operating in the linear region, and the graph between the collector current and collector to emitter voltage, which gives us the load line, the Q point operation has to be at the center of the load line in case of class A power amplifier. Class B amplifier, here the bias has to be done at the cutoff and it will conduct for half the input cycle. In class A amplifier, the entire cycle is used for the conduction process, but in class B amplifier, only one half of the input cycle will be used for the conduction. In cutoff, the other half will be present. So the other half will not be conducting. It is more efficient. So class B amplifier are more efficient than class A, but it has a problem of crossover distortion. Class AB amplifier, which is biased above the cutoff, it will conduct from 200 to 220 degree, which is more than the class B amplifier. So class B amplifier we have from 0 to 180 degree, whereas class AB amplifier is conducting above 200 degree to 220 degree. It reduces the crossover distortion, more efficient than class A. So in class B amplifier, we have seen here that it will cause the crossover distortion. So in class AB amplifier, it will reduce the crossover distortion and it will be more efficient also than class A amplifier. We have seen the push-pull arrangement of transistors in the previous lecture. So that will be used here in these type of amplifiers where two transistors will be used, one for the positive and one for the negative half cycle, and it will enhance the efficiency and power handling that will require proper biasing. So we will discuss this push-pull amplifier in detail little bit later. When we compare the class A, class B and class AB amplifier in terms of efficiency, we saw in the previous lecture that class A amplifier, the maximum efficiency is 25% and the conduction is for 360 degree, that is the full cycle of the AC wave, and it is having the best linearity and low distortion. However, it is inefficient and produce high heat, for which heat sink is required. Class B amplifier, the maximum efficiency is 78.5%. It will be conducting only for one half cycle, that is 180 degree. It will be highly efficient and suffer from crossover distortion. Now, what is crossover distortion? We will discuss a little bit later. Class AB amplifier efficiency lies between 50 to 70% and the conduction is greater than 180 degree but less than 360 degree. It has the advantage of balanced efficiency and the quality, but it is slightly complex in terms of biasing. So each amplifier has their own advantage and limitations. Let us start with the discussion on class B operation. So class B operation means the conduction is only for 180 degree. So given the input AC wave, the output what we get is basically conducting for 180 degree for the power amplifier and it is non-inverting. In class A amplifier, we have seen that although the input is amplified, but we get the inverted form at the output. So here the transistor will conduct only during one half of the AC wave. Output is also not an exact replica due to one half cycle amplification. So amplification is taking place for one half cycle, hence it is not the exact replica. Power dissipation, there is no problem when there is no input except there is a small amount of leakage current. Here the efficiency is higher than class A, up to 78.5%. In class K amplifier, again the efficiency is 25%. Class B amplifier commonly use push-pull common emitter follower circuit. About this we have discussed in detail in the previous lectures on transistors, biasing. We'll discuss on the power amplifier. So here we have the common emitter follower amplifier where the input AC wave, which has both the half cycle and the conduction, take place only for one half cycle. So we are getting the conduction from 0 to 180 degree, and other half there is no conduction. So up to 360 degree the transistor is off, and further we will get another half cycle of conduction. So push-pull arrangement, one transistor is amplifying the positive half cycle and the other transistor is the negative half cycle. We will see the push-pull circuit in the coming slides. Crossover distortion occurs due to a brief moment when neither transistor conduct at 0 volt. So the problem of crossover distortion occurs because two transistors in push-pull arrangement Q1 and Q2, so only one transistor will be on at a time. So the time when it changes conduction from Q1 to Q2, a slight brief amount of time will be there where there will be no conduction. So that period there will be a distortion which is known as crossover distortion. Class AB biasing is used to pre-bias this transistor above the cutoff and reduce that cross distortion. So in order to avoid the distortion, we can use class AB amplifier as a pre-bias in the transistor circuit. So let us see the push-pull operation of class B. So class B push-pull amplifier will consist of two transistors. Each transistor will conduct only for one half cycle of the input cycle, and the method is significantly to improve the efficiency as compared to class A amplifier. So since we are using two transistors, the efficiency is improved and challenges will be there in terms of crossover distortion. So here we have two transistors Q1 and Q2. These two transistors will be conducting for one half cycle, and the brief period for which it is not conducting, that will result in crossover distortion. There are two common circuit which we use for push-pull configuration. The first one is basically transformer coupled push-pull amplifier. So here we can see there is a input transformer and other one is the output transformer. So the input transformer is splitting the input signal. So whatever the signal is coming as AC, this is splitting into two equal but opposite signal because the secondary is center tapped. So we are basically getting two split signal of the input, and two transistors are in the NPN form. Each will amplify for one half cycle, and there is an output transformer that recombines the two amplified halves into full waveform. So whatever the output we are getting, this is amplified form of the input transformer signal. The advantage is that it provides signal phase shifting, but since we are using transformer, it will add the bulk cost and potential core saturation distortion. So this configuration, which is using transformer at the input and output, makes the circuit to be bulky and costly. The second configuration that we have is basically the complementary symmetry push-pull amplifier. So again we have two transistors Q1 and Q2, but one transistor is in the form of NPN and other is in the form of PNP, and these transistors conduct for one half cycle, positive and negative, one by one. It operates without an input transformer and hence it will simplify the circuit. In the previous configuration we have seen the use of transformer. It is not using any transformer, so the cost is less and simplicity is also there. It will require both positive and negative power supply. So we can see here that the supply that we give is plus VCC and minus VCC. So both positive and negative supply has to be there. This transistor Q1 will be conducting for the positive cycle and Q2 will be conducting for the negative cycle. So we are getting one half output. This is for Q1 and other half we are getting for Q2 conduction. So the positiveness is more compact and eliminating the need for bulky transformer. This is the pros. And the cons or the limitation is basically susceptible to crossover distortion, which is common in case of class B amplifier, whether we use transformer or whether we use two transistor in PNP or NPN mode. The crossover distortion is basically staying because the transformer stays off until the input exceed the base emitter threshold voltage, which is 0.7 volt for BJT. So here we can see that this is the positive half cycle of the AC input, which is conducted by the transistor Q1. This is the negative half cycle which is conducted by the transistor Q2. There is a brief time period where there is no conduction, and this time period you have certain distortion. This is because there is a base emitter threshold voltage of 0.7 volt which has to achieve in the network for the conduction that will result in the distortion. So a small gap in the output occurs when neither transistor conduct. So here both Q1 and Q2 are off in this time period and there is crossover distortion. These non-linearity cause distortion, especially in audio applications. Then what is the solution? The solution is to use the class AB type of biasing, which slightly pre-bias the transistor to conduct for small input signal. So before we apply class B amplifier, we should use a pre-biasing in the form of class AB, and this will reduce the crossover distortion while maintaining high efficiency. Class AB biasing will reduce the crossover distortion. It will eliminate the crossover distortion and it will achieve slight biasing the transistor into conduction even when there is no input signal. It means both Q1 and Q2 are off. Then also we have certain biasing, and it will ensure that both transistors are never fully off at the same time. So there is another one circuit where we can use two diodes D1 and D2. So here we have two diodes D1 and D2. This will provide a voltage drop matching the transistor base emitter junction. So this is the threshold voltage of 0.7 volt, which will be given with the help of the diodes D1 and D2. This pre-biases both transistor into slight conduction, avoiding the dead zone in class B operation. So class B operation, when there is a dead zone and crossover distortion take place, we can have certain pre-biasing with the help of the two diodes. And if these two diodes are thermally matched, then the current will become stable. The collector current which is flowing is in the class AB mode can be estimated using VCC minus the threshold voltage of 0.7 volt and the resistor R1, which is set the biasing level. There is a problem that if the transistor heat up, then the base emitter voltage will drop. That will lead to higher conduction and it will cause more heating. This will be the process of thermal runaway. So in order to avoid the thermal runaway, place the diodes close to the transistors for small thermal tracking. Add small emitter resistor to stabilize the current. So this solution if we do, then we can avoid the thermal runaway due to heating up process. If we talk about the AC operation and load line analysis, so the Q point again, which is at the center of the load line in case of class A power amplifier, this is different in class B. The Q point is at cutoff where the collector current is 0. So if you see the load line, so here you have the collector current and here you have the collector to emitter voltage. So this is the point where the collector current is 0. So if the collector current is 0 here, this is the point of cutoff. So class B amplifier, the Q point will be at cutoff. Whereas class AB amplifier, the Q point is slightly above this point to prevent the crossover distortion. And the collector current at saturation is obtained as the collector voltage by the load resistor. This is the maximum collector current during full signal operation. So this is the saturation level of the collector current, that is maximum. So the efficiency of class A, which is 25% maximum, is low due to continuous conduction, whereas class B, your maximum efficiency is 79%. due to transistor only conducting for half cycle, whereas class AB is a compromise between class A and class B. This is moderate efficiency with low distortion. We have seen two supply. Let us see the single supply push-pull amplifier where we are using only one supply, the other one is at ground board 0 volt. So it operates similarly to a dual supply amplifier. However, it uses one voltage source VCC instead of two. So this is only one supply. The key difference is how the biasing is set. So here you can see here there is input capacitors and there is one output capacitor. These are AC coupling capacitor, and it used to handle the DC shifting in case of push-pull arrangement. So here the biasing is done at mid supply VCC by 2 and the capacitive coupling will be requirement. So when we see the dual supply amplifier, the output was biased as 0 volt, allowing equal positive and negative swing. So we have basically plus VCC and minus VCC. So the output is biased at 0 volt. But a single supply amplifier, since we have only VCC, the output will be biased at VCC by 2 to allow both positive and negative swing. What is the reason? This ensures a symmetrical signal range for both the positive and negative variations. So the output is basically sitting at VCC by 2. The capacitors are used to block the DC. So the input capacitor and the output capacitor, which are the coupling capacitors, they will block the DC biasing from affecting the signal source and allow only the AC component to pass in the signal. Whereas the output one will block the DC component of the half of the AC from reaching the load, and it will allow only the amplified AC signal to pass. So the capacitor C1 and C2, which is used in the input as a coupling, will be you block the DC biasing, that is a full supply, and the capacitor C3, which is used at the output, will block the DC component of VCC by 2. The voltage swing, which is from 0 volt to VCC, this is for the ideal case, but the real world case, it may not reach this limit because of saturation of the transistors and voltage drop across the internal resistances. What are the advantages and disadvantages of these type of amplifiers? It works with a single power supply, so that is the advantage as compared to dual supply, making it more practical for many applications. It eliminates the need for negative voltage source, whereas the disadvantage, you are using capacitive coupling, which can introduce low frequency distortion and enable voltage swing is slightly lower than the dual supply amplifier. So the voltage swing is also a problem in case of single supply, and due to the use of capacitor, you will introduce low frequency distortion. Now we will compute the power and the other significant parameters of class B and class AB type of amplifier. Power output, which is the product of the output current and output voltage in RMS, and the output current we get as root 2 times the output current peak, which is again 0.707 the collector current saturation. So the output current peak is basically the collector current which is at the saturation. Similarly, the output voltage RMS is 0.07707, which is root 2 times the output voltage peak, and this output voltage peak is nothing but collector to emitter saturation. So this will come from again the load line. So here we are getting collector to emitter saturation, the BCE, and here we are getting IC, and this is the load line point what we have. So the output power in that case, if we compute by this equation, so that gives to be 0.25 times the collector current saturation into VCC, because collector to emitter VCQ is VCC by 2. DC input power is again the product of the collector current and collector voltage, and collector current is the saturation current divided by pi, because the current is a half wave signal with an average value of half the peak current. So only one half you have the conduction, so you are dividing it with pi. And the power, which is equal to the product of current and voltage, is also divided by pi. This is for the DC input power. Efficiency is nothing but output by input. So when we compute the output and divide the DC input we get 0.25 pi, which comes to be maximum as 79%. In class A, we were getting 25%. In class B or AB, we are getting 79%. So 70 to 75% we will get for both the type of amplifiers in general. Input resistance for this push-pull configuration will require two emitter follower with bias resistors R1 and R2, and we can compute the R input of this push-pull arrangement using the formula of parallel combination of R1 R2 with the parallel combination of beta times the current gain and sum of the resistors of Re dash plus Re. This calculation we have already done in case of common emitter transistors. So you can see the derivation from there. So this complete our discussion on class AB type of power amplifier. Previous lecture we have discussed class A, and in the coming lecture we will discuss the class C amplifier. So that will complete the entire power amplifiers. Thank you for now.